we are discussing the recursion, and last lecture we have learned how actually we can define recursively the sequences, functions and the sets. Today we will see in details with some examples that how recursively defined sequences can be formed and what are their applications. First we see the recursively defined sequences. We introduce an integer sequence which is popularly used in combinatorics and in graph theory. It is called the Fibonacci sequence. So, we introduce called Fibonacci sequence. So, first we see how these Fibonacci sequence are recursively defined. So, the recursive definition of So, as we discussed last day and we have defined the recursively defined sequences, functions and sets, that with some initial values and we can give some rule, so that we get a particular term in the sequence from the previous term or previous set of terms. So, Fibonacci sequence, it is defined that its initial condition, the initial condition or say f0 equal to 0, f1 equal to 1, where f represents the Fibonacci sequence and the recursive definitions are or I can tell recursive rule. That f n equal to f n minus 1 plus f n minus 2. That means, the nth term of the sequence can be found by adding the previous two terms. So, how we can find the sum of the terms using this recursive rule? So, since f 0 and f 1 are given, so if we find that find f 2, f 3, f 4, f 5, f 6, then I can apply the recursive rule as well as we take the initial values. So, f 2 is f 1 plus f 0 and f 1 is given 1, f 0 is 0. So, this is 1. Now, f 3 is f 2 plus f 1, just now we got f 2 equal to 1 and f 1 as the initial condition is given as 1. So, it is 2. Similarly, I get f 3, f 4, already we got f 3. So, f 4 is f 3 plus f 2 and f 3 is 2, f 2 is 1. So, this is 3. We got f 4 is f 3 plus f 2 and that is 3 plus 2 is 5. Then f 5 is f 4 plus f 3 is 5 plus 3 is 8. Then f 6 is f 5 plus f 4 is 8 plus 5 equal to 13. And if I continue in this way, we will be getting the values of the different terms of the sequences. So, in this way we can define the sequence recursively, we can define a sequence. Now, we can prove this sequence, that means the recursive definition of Fibonacci sequence in conjunction with the mathematical induction, we can prove, we can establish the some of the interesting properties using the Fibonacci sequences, and which has number of application in combinatorics as well as graph theory and other branches of mathematics. So, the recursive, using the recursive definition of the Fibonacci sequence, in conjunction with the mathematical induction. We can establish a number of properties of these sequences of this sequence. One very simple example we see. So, we see a property P 1. Say the property tells the sum of the squares of the terms of the Fibonacci sequence. So, just now we have seen the terms are f 0, f 1, f 2, f 3 like that of the Fibonacci sequence, and we have initial condition we have seen that f 0 equal to 0, f 1 equal to 1, and using the recursive rules we have found out that f 2 equal to 1, f 3 equal to 2, f 4 equal to 3 like that already we have seen. Now, we want to see that what is the value of the or the sum of the squares of the terms of Fibonacci sequence. So, if I write the say for I equal to 1, then it is sum of squares is f 0 square plus f 1 square, and this is 0 square plus 1 square is 1, and say I am writing this is 1 into 1. Now, if it is I equal to 2, if I equal to 2, then sum becomes f 0 square plus f 1 square plus f 2 square, and this becomes 0 square plus 1 square plus f 2 is also 1. So, again 1 square, that is 2, and this becomes 1 into 2. Say I equal to 3. So, similarly I can write f 0 square plus f 1 square plus f 2 square plus f 3 square is 0 square plus 1 square plus 1 square plus my f 3 is 2. So, 2 square. So, this becomes 6 is 2 into 3. Now, if I continue in this way, f 2 square plus f 3 square plus f 4 square, again this becomes 0 square plus 1 square plus 1 square plus 2 square plus f 4 is 3. So, 3 square, and this is 9 plus 6, this is 15, this becomes 3 into 5. Now, if we observe the results or the sum of squares for different values of I, what we see that we can write that it is for I equal to 1, 1 into 1. So, this becomes f 1 into f 2, because my f 1 and f 2 both are 1. Now, my f 2 f 3 is 2. So, I can write this thing as f 1 into f 2. I can write this thing as the f 2 into f 3. I can write this thing as the f 3 into f 4, this as the f 4 into f 5. So, we get a pattern. So, we can frame the formula that we can write that the conjecture or the result is that we can write the conjecture that for all n belongs to z plus that positive set of positive integers, the sum of squares of the Fibonacci terms that up to n terms, if I write this is f I square and that becomes f n into f n plus 1. So, this is first we see the property that what will be the sum of squares of n Fibonacci terms, and we get this formula. Now, we can prove this result by using the recursive definition and the principle of mathematical induction. As in the last lecture we have described that recursive definition is closely related with the mathematical induction, because the recursive rule that is framed from the concept of mathematical induction. Now, how we can prove that thing? So, we will be using the mathematical induction. So, if I get the proof, so first thing is that as we want to apply mathematical induction, so we have to write the basis step. So, for basis step we that for n equal to 1 we take assume n equal to 1. Then the conjecture becomes the n 1 f 1 square, or I write the similar way as it is written, that I equal to 0 to 1 f I square equal to f 0 square plus f 1 square, and from the initial conditions this is 0 square plus 1 square is 1, and that I can write that 1 into 1 is f 1 into f 2, since we know that f 2 is also 1. Since f 1 equal to 1 from initial condition, initial value or condition we can write, and f 2 equal to 1. So, my conjecture is true for the basis step n equal to 1. Now, we see the how we can prove the recursive step. Now, to prove the recursive step we use mathematical induction. So, we assume that the conjecture is true for I equal to n. That means, for I equal to 0 to n, f I square equal to f 0 square plus f 1 square plus f 2 square plus f n square, this is equal to f n into f n plus 1. Now, if we can show that this conjecture is true, assuming that it is true for I equal to n, the conjecture is true for I equal to n plus 1. So, for I equal to n plus 1, we have to show that conjecture is true. If we can show, then 0 to n plus 1 and this is f I square. So, I can write this is f 0 square plus f 1 square plus f 2 square f n square plus f n plus 1 whole square f n plus 1. Now, this is from f 0 square to f n square, I can replace by this summation I equal to 0 to n f I square plus f n plus 1 square. Now, already according to that principle of mathematical induction, it is the conjecture is true for I equal to n. So, I can write this is f n into f n plus 1 and the next term is f n plus 1 whole square. So, now if I take f n plus 1 common, then this becomes f n plus f n plus 1 is f n plus 1 into f n plus 1 is according to the definition of Fibonacci sequence, this becomes n plus 2. So, here I use the recursive definition of, here we use the recursive definition of Fibonacci sequence, and we use the principle of mathematical induction. So, this is f n plus 1 for I equal to n plus 1, it is true, it is true. So, I can write that the property for n belongs to, for all n belongs to the set of positive integers, that summation I equal to 0 to n f I square is f n into f n plus 1. This we can the proof, and in this way I can prove many such properties for this Fibonacci sequence. Now, we observe or some the importance of the basis step or the initial condition. So, how we define that Fibonacci sequence? We define the Fibonacci recursive definition that we have given, the Fibonacci sequence, the recursive definition of Fibonacci sequence, that with the initial condition f 0 equal to 0, f 1 equal to 1, the sequence is f n minus 1 plus f n minus 2. Now, if we change the only the basis step. So, this is my initial conditions or the basis step. I can write this is my basis step or my initial condition of the sequence. So, if I just change this, the even if the rule is recursive rule is same, then it will generate some new sequences. So, this is my recursive step. Now, one such new sequence we call the Lucas sequence. We see that Lucas sequence even if the recursive steps are same. So, here the recursive rule or step, recursive rule or recursive step is same as that of Fibonacci. Sequence. So, that means, if we can write that represent this thing as a L, Lucas sequence as L, then ln is ln minus 1 plus ln minus 2. But we change the basis step. Basis step is changed. We write the basis step is changed, or I should tell that initial conditions are changed. Initial conditions are changed. So, initial conditions we write that L 0 equal to 2 and L 1 is same as that of Fibonacci f 1 is 1. Now, if we see the sequences, we see the sequences and okay, right, this is my basis step. So, I can find out that L 2 which is L 0 plus L 1, this is 2 plus 1 equal to 3. L 3 is L 1 plus L 2 is L 1 is 1, L 2 is 3. So, this is 4. L 4 is L 3 plus L 2 plus L 3. So, this is 3 plus 4 is 7. So, we see that terms are even the recursive rules are same as that of Fibonacci sequence, but the terms are different. Here L 2 is 3, L 3 is 4, L 4 is 7 and the terms are different. So, if we prepare the list, we see the we can compare the sequences, the Fibonacci sequences and Lucas sequence you can, if we compare the values, we see that if we can put n we give ln and we give the fn and we see the different values of n. Say for n equal to 0, 1, 2, 3, 4, we take some more values 5, 6, 7 and we can see ln is 2 because it is given the initial conditions, then 2 plus 1 3, 3 plus 1 4, 4 plus 3 7, 7 plus 4 11, 11 plus 7 18, 18 plus 29. And here the initial conditions are different for Fibonacci, it is 0 and 1. So, it is 1, 1 plus 1 2, it is 3, then it is 5, then it is 8, 13 like that. So, what we see that this is my Lucas number and this is my Fibonacci number. See, even the conclusion is even the recursive rule or the recursive definition is same since the initial condition or initial terms of the sequences are different, they generate different sequences. Now, since the recursive rule is same, only the initial values are different. So, there is a close relation between the Lucas numbers and the Fibonacci numbers. So, we can see one property that again like we have seen earlier only the Fibonacci property. So, one property we have seen that where we give the relation, this gives some relation between Fibonacci sequence and Lucas sequence. I write one such property as the if I take the sum of Fibonacci numbers, I take Lucas number is I equal to I take a simple property that I can write the Lucas number say nth term of the Lucas sequence ln, I can write it is f n minus 1 plus f n plus 1. So, if I see the list of sequence, quickly we can see that my basis step is L 0 equal to 2, L 1 equal to 1. So, I can write, and the recursive definition, if I give recursive definition of Lucas number, we know that ln is ln minus 1 plus ln minus 2. So, I can write that it is, I can find that L 2, since L 2 is L 0 plus L 1, and we have seen already the numbers are 3 etcetera. Okay. And I can write 3 as 1 plus 2 and if we remember that this is f 1, I can write f 1 plus f 3 is 2, because if we remember the Fibonacci, f 0 equal to 0, f 1 equal to 1, f 2 equal to 1, f 3 equal to 2, then f 4 equal to 3, like that. So, what is my L 3? L 3 is L 1 plus L 2, and L 1 is 1, L 2 is 3. So, this is 4, and I can write that this is 4 is my 3 plus 1, that means f 2 plus f 4. If I continue in this way, L 4 is L 2 plus L 3, and this is my L 2 is 3 plus L 3 is 4, this is 7, and I can write that this is f 3 2 plus 5. So, f 3 plus f 5. So, I can write this is 2 plus 5, this is f 2 is 1 plus 3, this is also 1 plus f 1 is 1, f 3 is 2. So, I can see that the property holds, and the similar way we can write that. So, we can see that property holds for that ln is f n minus 1 plus f n minus 2, and the similar way we can give the proof also. We can see that for basis step, if it is for n equal to 1, that my L 1, or for n equal to 2, if I see that n equal to 2, L 2 is L 0 plus L 1 is 2 plus 1 equal to 3 equal to my f 1 plus f 3, 1 plus 2. So, it is true. And for recursive step, assume it is true for n, assume it is true for n. So, ln equal to f n minus 1 plus f n minus 2, true. So, for I equal to n plus 1, what I can show, ln plus 1 is L n plus L n minus 1. Now, I can apply the strong form of mathematical induction. Here we can use strong form of mathematical induction. So, that for Ln minus 1, for both we can apply the conjecture, and then for Ln it is f n minus 1 plus f n minus 2, and for Ln minus 1 it is f n minus 2 plus f n. So, if I take together the for Ln it is Ln is L 0 plus L 1 L minus 1 plus f n plus 1. Okay. This is L minus 1 plus f n plus 1. For n minus 1 it is n minus 2 and n. So, this becomes f n minus 1 f n plus 2 is f n plus 2 and n minus 2 and n minus 1 and n minus 2. This becomes f n and this becomes f n plus 2. So, which is the f n plus 1 minus 1 plus f n plus 1 plus 1. So, it is proved. So, we see that how recursively defined sequences can be defined, and for new sequences, and how we get the properties, how we can prove the properties using the mathematical induction as well as the recursive definitions of the sequence.